Assalamu alaikum. Good evening, ladies and gentlemen. Welcome to tonight's keynote lecture, The Solar Revolution. It's my privilege to introduce the new director of the Solar Center here at KAUST, Dr. Karl Leo. Professor Leo obtained his Diploma Physiker degree from Freiburg in 1985, working at the Fraunhofer Institute of Solar Energy Systems. In 1988, he obtained his PhD from the University of Stuttgart, and from 89 to 91, he was a postdoc at AT&T Bell Labs in New Jersey. From 91 to 93, he was at RWTH in Aachen, Germany. And since 93, he's been a full professor in optoelectronics at the University of Dresden. He joined KAUST in October of 2013. His main interests are novel semiconductor systems like semiconducting organic thin films, with special emphasis to understanding basic device principles and the optical response. He's won a large number of awards and has co-founded several companies. With that brief introduction, I'll turn the podium over to Professor Leo. Thank you.
Well, thanks, Bill, for the kind introduction. It's a great pleasure for me to step in here tonight and give this presentation. It was on short notice, and I had a talk prepared, so I immediately say yes. Later on, I found out that the talk I had prepared was in German, and I needed to translate it, which I did say 95%. If there are a few German phrases left, please apologize. Well, first of all, I'd like to express how happy I'm to be here. You know, it has been a great time for me since I started in October. People have been very supportive, and I think that KAUST and the Solar Center can really make a change in this region of the world. And it is, as you know, a solar region, and today I'm talking about a revolution which, at least in my personal opinion, is ongoing these days. Now, my outline is quite simple. Please allow me to say a few words about the Solar Center in the start. And then I'll make some rather general remarks on renewables. And the second part of the talk, which is the main part, will be on my personal research area, organic photovoltaics. I would say that about 60–70% of the talk are understandable for people who haven't studied science, but I will also delve a little bit into basic physics and chemistry. I will tell you when I start, and I will tell you when I stop, so you can take a little nap while I go into the details. Okay, let me start saying a little bit about the Solar Center, who I'm the director now. What's our vision? The vision of the Solar Center is pretty simple. We want to establish a world-class research program on 3 topics: photovoltaics, energy storage, and conversion. We have started with photovoltaics. In the mid and long term, we'll address the other 2 topics, because there was also already very good work on this topic, and we see that we must concentrate in the beginning on that. The other mission for us is that we have to train young people, because I recently noticed that there's a lot of new activities in photovoltaics industry in Saudi Arabia. There will be soon a module manufacturing plant in Jeddah, and there are furthermore investors coming. And we need to train the young researchers who work in these companies, and to collaborate with these people is our other important mission. The main photovoltaics technology we look at are so-called emerging PV. I'll define that in more detail later. We have strong work on organics, perovskite oxides, quantum dots, and on the copper-indium selenide materials class. And we have also a special point that we look at thin film photovoltaics, and we compare vacuum deposition and liquid phase deposition. And I would say this breadth of topics and this special comparison are really unique points about the Solar Center. Here you see some examples what emerging PV can do. It can be a flexible technology, it can be a transparent technology. I'll actually have some demonstrators with me, which I'll show later. Fortunately, there are a number of people in the Solar Center who do very strong work on PV. And in the future now, we have to further develop that, expand to some other areas missing so far, but I'm very optimistic that the solar center, after its somewhat late start, will quickly catch up and will meet what the financing people of this university expect and the Saudi society expects from us. Okay, so if you want to contact me anytime, these are my coordinates, but you can find me also on the web. Now to the general part about renewable energies. I start very simple. As said, basically, say 80 or 90% of our energy supply today is fossil. And what means fossil? Well, fossil means that hundreds of millions of years ago there were trees, even in Saudi Arabia. And these trees were decomposed over a very long time, and that is what we pump today as oil and gas. So it took a very, very long time, a significant part of the time the Earth is existing, to generate these fossil reserves, and now we burn them at a high rate, and sooner or later they will be finished. I'll discuss that in a minute, but it looks like, for me at least, that the generation of carbon dioxide is actually at the moment a more serious problem than the exhaustion of the sources, and I will argue why. As said, there's a big discussion when these resources are depleted. The keyword is so-called peak oil. It is known that any oil field has a peak and then it declines. And if you sum up all oil fields of the world, there will be sooner or later a peak. The main question is when. This is already a couple of years ago, and at that time people said it should be in July 28. It hasn't been. The main reason is that there are always new discoveries and especially also new technologies to exhaust oil fields. For instance, if you see, the US had actually a peak oil in 1970, but in the last few years, a surprise, it increased again. Some people say the US will be a net oil exporter soon. We'll see that. But for me, actually, as a physicist, thinking in basic terms, it is not really important when this will happen, because you have to look at it from a somewhat more larger distance to really understand what's going on. But one point I want to make is that, unfortunately, in the media, people don't step away and look from a larger distance at it. They look from a day-to-day perspective. You know, you read the newspaper in the morning, then you drive to the gas station, and people don't think long-term. For instance, to give you one example, a couple of years ago, there were newspaper reports that in Brazil, there were huge oil fields found. It makes Brazil to one of the largest oil exporters of the world, billions of barrels, and a big newspaper report. And in the next slide, I have a little quiz, which I'll make by public vote. When you calculate this enormous oil fields found in Brazil, how long can you supply the world's total energy consumption? So I give you 4 numbers, 21 years, 6 years, 1.2 years, or 30 days. And I ask you to vote by hand raising. Who thinks this might last 20 years? Few. Who thinks it's 6 years? Some more. Who thinks it's 1 year? A lot. And who thinks it's 30 days? Few. The right answer is 30 days. So all this big new oil field is burned in 30 days if you use it to supply the world's energy. You know, it should say in the article, this is enough to supply the world for 30 days, but unfortunately people don't look at it. So I made these diagrams to look at it from somewhat more distance. Many of you know that maybe 3,000 years ago or 2,500 years ago, there was the founding culture of the world, which was in Greece. And when you look at it from, say, a person who lived in Greece at that time, in the antique Greece, then this curve I've shown you before, you know, this curve suddenly looks like this. So for a long, long time, nothing is happening. Then we burn, and it's gone in a very short time. And actually, if you really look on a human scale, you must look on this scale. You know, this was one of our first ancestors in Africa 3 million years ago, Lucy, or how she was called. And if you look at the perspective from Lucy, actually when you plot this line here on the computer, due to the resolution, the line is 1,000 times too thick. So what we actually do is that we burn, given the fact that these fossil reserves were generated in 500 million, not in 3, much, much to the left, in an incredibly short time, we burn what has been produced in a very, very long time. And I think that is maybe not a very good idea. And the solution for this problem is the sun. So let me say a little bit about the sun, what the sun can do, what's the physics behind it, and how much of the sun do we need to avoid this burning. As you know, the sun is actually based on the insight of Albert Einstein that mass and energy are equivalent. What the sun is, it's a nuclear fusion power plant. I'm sometimes surprised that leftist parties don't complain about the sun because it has absolutely no security measures, no confinement. There's a nuclear reactor burning, but fortunately it's far away, so it's not a problem. The numbers are impressive. The sun actually burns per second 4.3 million tons of hydrogen to supply sunlight, but it's that big that it will last another 5 billion years. So sooner or later the sun will also be not renewable, but it's a long time on a human perspective. Now let me come back to this problem of the carbon dioxide and the greenhouse effect, global warming. If you read the literature about it, it's extremely difficult to find a clear opinion. There are many people who have very good simulations who say we have a global warming problem. Other people completely ignore it and say carbon dioxide is actually good for plants and this is all nonsense. I don't want to get into these arguments. If you look at the physics of these climate simulations, they are extremely complicated. And for me as a physicist, if you want to find out whether a theory is correct or not, what you do is a control experiment. You take a system without an effect and then you check whether it's gone. Unfortunately, and that is the bad reality, we have no control experiment because we do this experiment of climate change with the only Earth we have. We don't have a second Earth to test it. And this is always a bad idea if you have only one system doing an experiment with unknown end. There are other arguments. Actually, when you take the energy flow of the sun, which is actually about 1 kilowatt per square meter at full sun outside, and you do the radiation balance, assuming that there is no atmosphere, you find out that the average surface temperature of the Earth would be minus 18 degrees. That means without the atmosphere, without greenhouse effect, it would be really cold. And it's the greenhouse effect which increases this by 33 degrees Celsius and brings us to the more cozy 15 degrees. And if you look now at the CO2 curve over a long time, this is all natural cycles, ice ages, and this is human. Within a couple of years, we are changing massively the CO2 content of the atmosphere. Knowing that the CO2 content is extremely important. If this raises by 5 degrees or goes down by 5 degrees, we have a significant problem. So my simple argument is, given these numbers, it is simply not meaningful to accept this. But, the reality is that I'm personally pretty pessimistic. Since it's a worldwide problem, we have to adapt to it. I don't really expect that all these Kyoto protocols will help a lot. Now, the next question I want to address is there enough sun to provide the world with its energy consumption? And the answer is very clearly yes. These cubes show the ratio of the yearly world energy consumption and different sources. These are actually the fossil sources and uranium, and the total, sorry, there's a misprint, the total established reserves. So as you can see, coal is about the largest, and if you take these two cubes in relation, you have about 500 years. So there's plenty of coal for hundreds of years. Oil is less, gas even less, and also uranium is not very far-reaching. If you would take all the energy from uranium, it would be depleted in about 10 years or so. But you see, every year the sun is actually supplying much, much, much more than we need, and it would be, given the ideation, absolutely no problem to fulfill all our needs. It's instructive to compare the different renewable sources, and actually what I compare is the sun. Sorry, here my translation mistakes show up. This is the sun, which produces 80,000 exajoules per year. Exa is a very high power, which we don't really need to know at this point. The main point I want to make is if you compare it, say, to wind, biomass, and water power, you see the numbers. So when you compare renewables, it's solar and then for a long time nothing. So all the other sources, if you take sources like tidal waves or so, are even smaller. So the sun is by far the largest renewable source. There's another interesting point, and here I actually repeat what Hartmut Michel said last week, and this is the question if we compare, for instance, the sun to biofuel. And I found a very instructive calculation from a magazine. Unfortunately, the diagram is in German, but it's not hard to understand because the languages are so similar. What they did in this graph is that they actually assume that you own a field of 100 by 100 meter, which is a little larger than a soccer or football field. Actually, assume you own that. If you now grow biomass on this field, say either for diesel or for gasoline, and you want to drive your car with it, you can actually drive about 20,000 kilometers. That's on the average what a German drives. So every German would need 100 square meter to drive what he drives every year. However, if you instead put photovoltaic cells, silicon or other solar cells onto this 100 by 100 square meters, you can drive 3.2 million kilometers. This is a factor of, I think, 160. In other words, if you own area, it is completely meaningless to make biofuel. If you have leftovers from processing or from wood or so, it makes sense. But just growing biofuel for generating energy is unfortunately nonsense. And if you grow it in an area where you could also grow food, it is actually, if one is harsh, it's a crime. And for instance, the revolutions in the northern African countries in the last few years, they were linked very much to the price of food. And the food price grew because the Europeans, and especially the Germans, are currently in a biofuel frenzy and buy all over the world food to make biofuel. Complete nonsense, and it's really very bad that this happens. And as Hartmut Michel said, somehow in politics, science is not really taken seriously. Now, to further visualize how much area you would need to fulfill all the world's energy supply by solar, when you do the math, it actually turns out that an area of 900 by 900 kilometers square is enough. And as you see, I put it now on the Arabic Peninsula. And even in Saudi Arabia, the area we have as desert is by far enough. You could supply all the world with 900 by 900. If you want to do all the electricity, you need 400 by 400 square kilometer. So the supply of the sun is obviously by far enough. The problem is really pricing and distribution. I mean, if you want to distribute electricity all over the world, you have a problem. Some of you might know about the so-called Desertec project. A couple of years ago, especially in Germany, people had a very smart idea, or something they believed to be smart. They said, why don't we make a big network all over Europe and Northern Africa and Arabia of different plants, solar plants, and we connect them all. And we have here in Europe now a safe and secure renewable supply. That idea actually took off, and many German companies invested some money into it. It came very quickly to a standstill when these images were shown on German television screens. You know, people quickly realized that in countries which are governed by people like this, you can't invest billions, and you cannot make very expensive transmission lines through the Mediterranean if you can cut them actually very easily in Northern Africa. So this Desertec project came to a standstill, and it shows that in energy you cannot really separate policy, you have to do both. Okay, now I'm switching to organic photovoltaics, and I start with showing what the status quo in photovoltaics is, and that is actually silicon. It's more than 90% market share. You have pretty much, all of you have probably seen such modules. To give you a number which you should keep in mind, you need about 200 grams of silicon, very high purity, very expensive silicon per square meter. You need very high temperature processing to make these cells, and you cannot do flexible and transparent solar cells. So that's where the organic semiconductors come from. Organic semiconductors are a new class of semiconductors. They are very different because they are prepared not as little crystals, but they are from the beginning made on large area and flexible. They are basically based on carbon, so there's plenty of carbon around, and you need 1 gram per square meter. Compare that to 200. So the amount of material is much, much lower. And you can do a number of nice things. You can do not only solar cells, but also organic LED, transistors, and further stuff. We have seen applications of organic LEDs. If you own a Samsung Galaxy phone, you actually use an organic LED display. And one of the facts which I'm very happy about is that actually Samsung licenses some of the patents I did with my colleagues on organic LEDs. Organic LED TV are not really frequent. You can do lighting, and what I want to talk about today is organic photovoltaics, and later on we'll also see transistors, for instance, in these kind of displays. Now, the physics of the organic semiconductors are fairly simple. This is still high school knowledge. What you basically take is carbon, and carbon has the very special property that it has an unusual variety of bonding schemes, and especially you can make the so-called pi bonds. And these pi bonds have an energy splitting between bound and unbound states, which is invisible. So many colored substances in nature are actually these carbon substances with the pi bonds, and for instance, most of the dyes we use for colors are also organic semiconductors. And you know them actually from everyday life, these materials, and jokingly I'm showing this slide. If you drink a modern soft drink, you are also drinking organic semiconductors. For instance, this is a typical soft drink colorant, which is actually, as you see, a carbon compound. And when you look at the optical spectra of these materials, they look very similar to these materials we take for organic solar cells. We have never tried to make an organic solar cell from one of these soft drinks, but definitely you could do it. It's worth to mention that this carbon physics and chemistry is very rich. I will talk mostly of molecules which are zero-dimensional, small molecules, like this soccer ball molecule, but there are also one-dimensional tubes and two-dimensional sheets. This is the so-called graphene, which is a new wonder material, and I'm very sure it will be introduced in microelectronics soon. The really important number of a semiconductor is the so-called mobility. And actually, when you look at these organic materials, they're actually pretty bad semiconductors. Their mobility is about 5 orders of magnitude lower than silicon. But if you do the calculations, actually it turns out they are good enough for solar cells. It's also worth to mention that these organic molecules form beautiful crystals. These are some images taken by one of my spin-off companies in Fairfax, and it's really fascinating to look at the crystals formed by these materials. But as mentioned, the mobilities are low. The best mobilities achieved with organics are approximately where amorphous silicon is, and this is still a factor of 1,000 below silicon wafers. And the mobile phone in your breast pocket is typically at a mobility which is even orders of magnitude below, but still it's an efficient device. So for these applications, the mobility is good enough. As I made before the point that you need half or 1 gram, I should have corrected that. It's approximately 1 gram per square meter. The reason is that when you make such an organic device, this is for instance an organic light emitting diode where you put an organic layer between two contacts, the one is transparent, that it's actually interesting to realize how thin these layers are. With permission of Jean-Marie Basset, I took the Eiffel Tower from Paris. And when you scale the substrate, which is maybe 1 millimeter here, to the height of the Eiffel Tower, 300 meters, the organics layer is now 3 centimeters, whereas the human hair would be 18 meters. So for these solar cells, you can take incredibly thin layers on the order of 50 to 100 nanometers. So they are many, many orders of magnitude smaller than human hair. And the big advantage now when you have these very thin layers is that you can make them flexible. You have a very low material and energy consumption. You have a very short energy payback time. I'll come to that in a point. You can make them transparent. and you can make them cheap. And I brought some demonstrators. So the one I brought is a flexible fall demonstrator, and it's actually transparent. It's about 25% transparent, which is what you need for building integration. And if I see all these glass walls at KAUST, it would be wonderful to have a transparent solar cell in the facade, and you could generate a lot of energy. Let me now show where organic solar cells are. This is a very complicated plot. You don't need to look at the details. What it basically shows is the efficiency versus time for many, many different solar technologies. The most important one is actually standing still since about 10 years. This is silicon at about 25%. And I'm talking today about technologies which are still here down in the noise, so to speak, below, say, 10% or so. But as you see, these kits are quickly growing, and that makes them interesting, and I'll come back to the point how quickly they will grow. Energy payback, what does it mean? Well, if you manufacture a solar cell, you need energy. When you deploy it to the field, you get this energy back, and obviously you must get it back in a time which is much shorter than the lifetime of the solar cell. When you calculate the energy payback, and I took here German data, which means pretty little sun, you see that many of the other solar technologies need several years of insulation before you have the energy back. Whereas for organics, if you have only reasonable efficiencies of a few percent, you are already at 1 year in Germany. And if you go to a high efficiency, which we can reach, you can actually see you can get energy payback times which are in the region of 1 or 2 months, even in Germany. So the often used argument against photovoltaics, they waste more energy in production than you get back, is absolutely not true, especially for organic PV. Now I'm starting to go a little bit more into physics. As said, I apologize to all of you who haven't really studied that, but I'll tell you once I'm finished. The physics of an organic solar cell is actually much more complicated than a silicon solar cell. The main reason is that you generate so-called excitons, tightly bound excitations, and it's difficult to transport and difficult to separate them into charges, and that's what is challenging in these organic materials. To give you a number, these excitons, these photo-generated excitations, they diffuse only about 10 nanometers till they are filled. In a silicon solar cell, they typically diffuse 500 micrometers, but in organics, the diffusion length is very short. We've measured that, and there's various solutions, and for instance, in this material, it was 10 nanometer. The other problem is the tightly bound exciton. And what does it mean? When you generate an electron in a hole, actually in an organic material, the binding energy is about 0.25 electron volts, much, much larger than KT. Whereas, for instance, in silicon or gallium arsenide, the binding energy is smaller than KT. So you really generate a tightly bound pair, and it is not easy to separate it. You must take a special measure. And the special measure is actually invented by Jing Teng in '86. Is to take a so-called heterojunction where you have two different materials. So you generate the exciton, it diffuses to the interface, and there it's separated. So there's a lot of interface physics in chemistry in organic solar cells. The other problem, as I said, is that it can diffuse only 10 nanometers, which is very short. And if they cannot reach the interface, you have to bring the interface to the exciton, and this you do by mixing, intimately mixing the two compounds, the yellow and the blue. And you generate a nanostructure which is on the 10 to 20 nanometer scale. To generate this and to control this is very challenging, and this is the major problem in organic PV at this time. Now, it depends all on the molecules you are starting with, and in the last few years in Dresden, together in a collaboration with the University of Ulm, we did, I would say, the first really very systematic study for this class of molecules, where we looked at the influence of the molecular structure on the morphology of this so-called bulk heterojunction. And we had a number of molecules. As you can see, we had molecules where we changed the number of these thiophene rings. And we had other molecules where the number of thiophene rings was constant, but we changed these side groups. And in total, it was a large number of compounds. When you look at the energy levels, it actually turns out when you change the number of the rings in the molecule that the highest occupied orbital, the so-called HOMO, is changing quite a bit, whereas the LUMO is unchanged. But you see another effect if you change now the different side groups for a constant number. This is the different here. You see that the energy, this is the energy in the solid state, the red number, is actually changing quite a bit in dependence on the side groups. If you measure the molecules in solution, it is not really changing, but in the solid state it changes, which tells you that these molecules pack differently in the solid state. You sit like putting Lego stones on top of each other, you make a solid, and obviously the packing depends a lot on these side groups. So it's obviously a quite complicated system, and we looked actually at three molecules in more detail, those three molecules, which are very similar except they have all methyl groups but at different positions. And when we made solar cells, it turned out that the efficiency was quite different, and the one molecule, the compound number 3, with the methyl in the center, was actually by far the best, and we said, okay, this is the best molecule, and obviously this has the best packing. Now we published that, but later on we learned that things are more complicated. We repeated the experiments first and showed that this is really repeatable, but then we did more detailed measurements. We went to the synchrotron source in Stanford in California, and we measured the morphology of these layers in more detail. And actually what you learn is that the materials are pretty much amorphous at room temperature, and at higher temperatures they get crystalline. I don't want to discuss these figures in detail. But the main difference between these molecules is actually, as we learned, is that the temperature at which they get crystalline is quite different. So what it turned out is that the one molecule is getting highly crystalline at 110, whereas the other molecule needs 140. So only a small temperature difference while you deposit these layers is changing the morphology dramatically. And at the end, we could really understand what's going on. We have these mixed layers on a nanoscale layers, which are amorphous and smooth. And then we start to heat them. They get more crystalline. They get rougher, and the efficiency goes up. And when you go to too high temperatures, actually then it goes down again, but the region where you reach the good quality is actually only a little bit different by 30 degrees, but that was already enough to mislead us and to come to the wrong conclusion that one of or the other materials is better. Actually, at the end, both are the same if you treat them the right way. And we learned a lot. This is further morphology, which I can't really discuss. Okay, this is now the end of the real scientific part, so if you have taken a short nap, wake up now. I'm coming now to the question, what is the efficiency of these organics? And for this reason that the exciton is difficult to separate, the efficiency in organics is typically lower. We did some calculations for standard solar cells, and what we found out is that in the ideal case, when you do everything right, you can get a maximum efficiency of about 15%, which means that if you make a commercial molecule, you have 10 to 12. As I said, silicon is today at 20 or 25. This is simply not enough. So we looked what happens if you take two cells stacked on top of each other with different gaps, if you use the full solar spectrum. And then the numbers get better, and you see that more than 20% are possible. And the goal we have to reach is now to make these 20% possible. We did quite some experiments on stacking these cells, and as you can see, these structures get fairly complicated. You deposit in this case, and this is also the case for these modules, you deposit typically about 10 layers, and some of these layers are 5 nanometers thick. However, with the evaporation technology we use, this is not that difficult to do. And the best value obtained so far is by our spin-off company, Heliatech, which has now achieved 12% a little more than a year ago. 12% is actually, for organic solar cells, a very good value, but again, we can compete with silicon. What can we do? The first point we have to keep in mind is that these 12% are actually better than they sound. First of all, if you look at the historical development of the organic PV, you can see that for a long time it was fairly bad. Even the certified larger cells for a couple of years ago from Japanese companies were at around 3%. But then in the last few years, it really took off, and today organic PV is in the range of other thin film technologies. As said, at 12%. But the main point I want to make is that these 12% are actually better than you think, because the 12% are measured under standard conditions, laboratory conditions, which means 25 degrees. And this is not true. If you put an organic solar cell outdoors, even in the summer in Germany, it has 45 degrees. In Saudi Arabia, it probably has 60. And when you take that into account, it actually turns out that organics is better than you think. We call it the O factor. It's not only temperatures, it's also intensity and spectral light or diffuse responsivity. At the end, it turns out that organics is 30% better than the standard measurement says. To give you an example, if you take the temperature data, this is the standard technology, amorphous silicon, CHES, crystalline silicon, which goes down with temperature, whereas organic goes up, and you can see you gain at the end about 15 to 20% already by temperature, and by these other effects about 30%. So these 12% actually, they would come close to a 15, 16% silicon module easily outdoors. So we are now in the ballpark where we need to be. The next question, which is always asked, this is organic, this is carbon, does this have a long lifetime? And I show you first some data which were actually taken in a scientific environment by my PhD student, Christiane Falkenberg. She was not looking for a long lifetime, but for different electron transport materials. But what she found is that when she aged a cell under the concentration of 2 suns, it simply didn't want to age. And finally, she made a lifetime extrapolation very roughly, and the result was that the lifetime of this cell would have been 37 years outdoors in Germany. In Saudi Arabia, maybe shorter, but basically what it tells you is that these carbon materials are quite long-lived. You have to block the UV radiation, which is possible, and it's not generating a large loss. And when you look at now the commercial products, the flexible modules, they easily match now this damp heat test, which is required for photovoltaics. You have to have a lifetime of 1,000 hours at 85 degrees and 85% humidity. And as you can see, these organic modules are basically not aging. So the lifetime problem can be solved as well. How do you produce these cells? The way you produce them is quite interesting. You take a plastic foil, which you can see here on these wheels, and then you pull this plastic foil around a big cylinder, and around this cylinder you place organic sources, and you evaporate all these layers in one shot. You wind it once around and you are done. And I brought one module. If you later on want to take a look at it, you can come to the stage. This is actually a test module which was produced on a similar tool like this by Heliatech. And you see it's flexible. It has an attractive dark green color. You can also make it blue. And we want to test this module now at KAUST and see how it does in the desert. So in the future, technology will be solar technology will be such a foil, and you can imagine that there are many ways to apply it where classical silicon cannot be really applied. This is an example where we manufactured actually at the Fraunhofer Institute, where I worked as well, where we manufactured organic LEDs on the foil. This is for OLED lighting. And actually, if you do the cost calculations, lighting has about the same requirements as solar cells. And the applications of this organic PV, this is a slide also taken from Heliatech, are various. The first really interesting market is actually automotive. For instance, if you have a sunroof in your car, you can very nicely put a transparent organic module into it, and you can generate a little bit of electricity to recharge the battery. And I think the biggest further market will be building integrated PV, where again this transparent technology is superior. But I personally believe that if you really want to achieve a big success for organics, we have to go to the power plants, to the energy generation market, and at least the potential is there. It will take at least another 10 to 15 years of research, but the possibility is there. Now I want to conclude to talk a little bit about energy generation cost, because not long ago there was really something which I think one can call a revolution. The main point, or the most important point in photovoltaics is the cost, which is euro or dollars per watt peak. Watt peak means under full sun. And as you can see, in 1980 or so, you talked about 20 euro or so. It was extremely expensive. And over many years, there has been a dramatic learning curve, and the learning rate is actually 19.6% per doubling of the production. And as you can see, in the last few years, actually, the learning was even faster, and we have now module prices which are well below 1 euro, or even also below $1. So we have more than 20 or 30 times reduction in the last 30 years. And what does it mean in terms of electricity prices? Currently, in top locations like here in Saudi Arabia or in Northern Africa, you have a kilowatt hour cost of about 10 US dollar cent. In Germany, you have about 20 US dollar cent. And since in Germany, if you buy electricity retail, it costs you 25 euro cents. So in Germany, for the first time since we ever have solar energy, you don't need a subsidy anymore. You buy a solar module, you put it on your roof, and you make a profit. And even for big power stations, this is the case. I recently heard a talk from a company which made a plant in Chile in the desert, and they have a generation cost of 8 cents per kilowatt hour, and in Chile this is sufficient to sell it to the grid without any subsidies. So we have now the situation that subsidy-free feed-in is possible, and together with the fact that we should see at least a further reduction of 2 in these prices, I think it's fair to say that photovoltaics will be in the midterm future, long-term future, the cheapest way to generate electricity, cheaper than coal, oil, gas, or any other technology. The problem with storage has to be solved as well. Transport is part of it, but storage is another problem. But in the time I had tonight, I couldn't really discuss storage. I want to end with one slide which is intentionally in German because this was a German person who came to that insight. And it shows you that even more than 200 years ago, there were some people who had insights which many people even today haven't grasped. The person I'm talking about is a German poet called Novalis. His real name was Friedrich von Hardenberg. And his job was actually that he was working in the forestry department of the Saxonian states, right close to Dresden, where I'm today. He was working in the forestry department, and he observed that at that time people used too much wood, so they couldn't supply enough wood. And they have started to use Erdkohle, which translated would mean soil or soil coal. In other words, they started to use coal 200 years ago. And he said his job was now to find more of these Erdkohle so that the wood wasn't used anymore. But after a couple of years, he realized, this is stupid to take this Erdkohle, because only a few years later, he realized that we actually neither need Holz, we neither need wood or coal, because in a few years, you can actually use the sun. At that time, it was to make salt, to cook salt for salt fabrication. And he said, let's do it with sun, then we don't have the wood problem, and we don't have the coal problem. We can do it all renewable, and that was 200 years ago. And that brings me to the end of the talk. If you really look at the history of the energy supply of mankind or humankind, we had a renewable age. It was basically a wood or sun age. We have a very short time, which is today, where we waste our resources and ruin the climate. I'm part of it, I'm flying a lot. And sooner or later, we'll have a second renewable age. It might take 20 years, it might take 50 years, it might take 100 years, but it's absolutely guaranteed that we'll enter this age, and it will be fun to work on the science to reach this age. So that's all I wanted to talk about today. Here are some sources. Sorry, it's hard to read. And thank you for listening to me, and I'm glad to answer questions. The question is, what's your opinion on nuclear energy sources, especially fusion? Well, you know, I'm working on photovoltaics since many years, but I'm one of the few people working in photovoltaics who believes that nuclear power makes sense at the moment, and I think it's a disaster what's happening in Germany, that people switch off these sources and replace them by coal. It's a transition technology, but it makes sense. In terms of fusion, it's a very difficult question. There's this old joke that fusion is the energy source of the future and will be all the time, or will remain, you know. Since about 50 years, people tell us that fusion will be ready in 20 years. And I heard once a talk from a person who knew fusion very well, and he made a very critical argument. He was fired from his institute who works on fusion because of these arguments. He said, if you look at a fusion plant, the energy density of a fusion plant is 10 times larger than a fission plant. Fission is a very compact reactor, a fusion plant is very larger. And he said, if the plant is 10 times larger, the energy generation cost, which is in fission basically the investment, will be 10 times larger, and then it will not be competitive. So he said fusion doesn't make sense because it will not be competitive. And if you see the prices for solar I've shown in the end, I doubt it. But it's a technology which works round the clock, and I wouldn't disregard it. Yes, sure, there are other renewable energies, but as I showed in the beginning, their potential compared to solar is very small. There are some countries like Norway, which basically live from hydropower, or Iceland, which live from geopower, but these are exceptions. If you really look at most of the countries of the world, the main renewable source has to be solar, simply because the other sources are not large enough in supply.
Thanks. Here. Sorry. My question is about what do you think about the possibility to have the solar cells to alimentate the house at KAUST? I not understand really why we not use at KAUST this kind of energy. Thank you.
I fully agree. Actually, for me, it's a little bit difficult to understand that KAUST didn't do two things. The one thing would have been to power KAUST largely by solar cells, which would be actually quite easy. And the second thing I can't understand, you know, if I ride my bicycle in the morning to work and people in the SUV are passing me to drive 3 kilometers from their home to the university, I wonder really why KAUST wasn't done as a model for electromobility, because electrical cars would be ideal on this campus. I don't know why. Maybe that's a task for the future.
And sorry, but the cost to convert the house to an energy sustainability is higher, or is something that could be done in the future? Sorry.
The electricity pricing in Saudi Arabia, to my knowledge, is about 3 cents per kilowatt hour, which is probably the lowest in the world. As I said, we are typically for residential, under these sun conditions, we would be at about 10 cents. So electricity is too cheap in this country.
Thank you.
And gasoline, and hence the SUVs to work.
Gasoline is even worse.
Yeah.
Yeah, the question is, when do we see organics in the market? There was a company, Konaka, in the market and failed because it was too early. In my opinion, in the next 5 years or so, we'll see only niche applications, you know, sunroof for cars and maybe some camping applications. You know, I work now for photovoltaics since 29 years, since my diploma thesis. And the one thing I learned is that photovoltaics is a very difficult technology. It needs to be really cheap. It needs to be large area. It needs to be very long lifetime, you know. A typical mobile phone is thrown away after 2 years. And a solar module must make 20 or 25. So technologies take time to mature. And therefore I say we need, for a broad distribution, at least another 10 to 15 years of research. There are significant problems of organics not yet solved.
I have a question. Sorry. Is it safe to say that solar is entirely renewable? Because, for example, I'm just wondering, because there's various substances inside, for example, the silicon substrate, for example, the cost, the way it's made, I've heard it's pretty, it could cause pollution, the industries in China and all that they use to produce these substrates. And also, I think there are various rare earth metals that could be used in these photovoltaic cells. And, well, as the name says, they are rare. So there's already a dependency on certain countries to get these various substances. And can you safely say that there won't be a dependency on these substances, and how far can we keep producing these photovoltaic cells? I don't know, as you say, a few thousand years here, but I'm just wondering.
Yeah, the resource problem is a significant one in photovoltaics, and actually most of the systems on the market have one or the other problem. For instance, the typical silicon solar cells have silver contacts. But I think these problems can be solved, and especially for these organic modules, they still contain a little bit of metal, but it's only a matter of time till even the contacts which contain the metal can be replaced by carbon-based materials. So basically, in 10 years, such a module will contain carbon, a little bit of nitrogen, and maybe sulfur, hydrogen and oxygen, and these are all elements which are not a problem.
My question is a sort of follow-up to the gentleman's question just a moment ago. I was wondering, because we're all constantly hear about organic and non-organic photovoltaics getting better and better and better every year, but they actually use different materials to make it. For example, non-organics use arsenides or galliums and so forth, while organics, as we were just saying, they use rare earths, etc. So the question is anybody looking into how to recycle all of these materials, because they will last for 20 to 40 years, but afterwards what we will do with them, right? So is anybody looking into how to recycle all of these?
Yes, that is indeed the case. Even for silicon modules, people have started to recycle the cells. Even in production, when the cells break, the silicon is recycled. The most prominent thin film technology at this time is cadmium telluride. And when you buy a cadmium telluride module from First Solar, there's a big sticker on the back which says, please recycle and contact our company. So yes, it is indeed possible. I mean, if you make a fully carbon-based module, recycling is not really an issue. But for the inorganic technologies, recycling is an issue. The main problem nowadays has been that since the lifetime of these modules is very long, typically the company are long gone when you have to recycle their modules.
During your presentation, you said that we should, you suggested that we build the solar cell power plant in the desert. But we all know that there's a huge problem in the desert is the sandstorms. How that will affect the solar cells. So how we can deal with this problem?
Yeah, a very good point. I didn't have time to cover it, but it's actually one of the points we work on at the Solar Center. If you have a standard solar cell plant in Saudi Arabia and you do not clean it, after about a year you are down to 50 or 60% of the power. And that means you need to regularly clean it, but unfortunately you usually don't have water available. And this problem is at the moment not really solved. There is one quite interesting approach from a spin-off company here at KAUST from Nomad, which makes a cleaning robot going up and down the module rows and cleaning it, and they have shown this works. The more elegant approach, and we work on that, is to coat the solar module with a layer which actually prevents that the sand accumulates. But it's a severe problem, and it's actually for photovoltaics a little bit better than for these thermal solar plants, because these thermal solar plants are working with mirrors and are imaging, and they had terrible problems. They had to clean the mirrors all the time, and it's expensive and is a major cost factor.
Yeah, hi. So I have one question regarding the costs and prices of the solar cells. So as far as I know, the costs and price of solar cells have been dropping significantly in the past 20 years or so. But in 2010, something interesting happened, and that is the prices actually dropped significantly, and it was very steep. So as far as I know, it was because China basically started selling their solar panels at very cheap prices. But I'm not sure how they were actually able to go this low. And as far as I've read some articles, and they were saying that they started, selling them at prices lower than the cost, which makes no sense to me. So my question is, what other companies are doing right now to compete with these, solar panels from China? And how did China actually do it? I mean, how did they succeed? Thank you.
You make a good point. Actually, if you look along this learning curve, you can identify some of these effects. This effect is actually the effect that due to the German feed-in tariff, there was a shortage of modules for a couple of years, and the area above the red line has been basically paid by the German taxpayer, because the companies made huge profits because the modules were really expensive. Then suddenly the capacity was too large, and in the last few years this effect here is that the Chinese manufacturers had more financial power, more subsidies than their European and US counterparts, and they actually sold for a long time under price. And just in these days this underprice selling is stopping because the technology has developed. And I have heard numbers that in 2014 you can make modules for about 65 US dollar cents. So approximately at this point you can still make a profit. And there are projections that you can even with silicon go down to 45, 50. But the fact is indeed that this is a field where subsidies play a big role, and for the moment most of the manufacturers are now in China because the government has subsidized the manufacturers most strongly.
After absorbing the sunlight energy, the electrons of the organic semiconductor jump to the higher energy levels, so which is a specific process.
Sorry, I didn't really get the question.
After absorbing the sunlight energies, the electrons of the organic compounds jump to the higher levels. So which is a specific flow of electrons in this process?
Yeah, that's the elementary process, that you generate an excitation which moves the electron from the highest occupied state to the lowest unoccupied state. And that process is very similar in silicon or organics. The main difference is that when you do that in silicon, the electron and the leftover hole are only weakly correlated, and you can directly put them to the contacts and generate a current, whereas in the organics they are tightly bound and you have to separate them. And that is the reason why organics has typically lower efficiency.
Okay.
You gave a very nice talk, a little bit oriented toward your field. But if you look at transportation, of course you can have cars working with electricity. But if you go to the planes, the transportation of planes will not, to my opinion, be solved by electric energy. What do you believe? What is the solution for planes?
You are absolutely right. The energy density of batteries or solar cells is not large enough for planes. And for planes you need probably a hydrogen solution. So the solar economy, in my opinion, will most likely be a hydrogen economy. I mean, if you look at cars, there was simply recently a calculation. If you have a garage with a roof, the energy you generate on the roof is enough for the average driver in Europe or the US. So all the solar cells you have on the battery of your garage, on the roof of your garage is enough to charge your battery. But for air transport and for trucks, it's not sufficient. And we also need renewable fuels.
Okay. Well, let's thank Professor Leo again. And,
Thank you.